Okay, you're seeing your first very big and hairy program. Now, of course, one of the goals of this subject is to get you to be able to read something like this and not be afraid of it. This one's only about 4 pages of code. By the end of the subject, I hope a 50-page program will not look particularly frightening. But I don't expect, and I don't want you to think that I expect you to be getting it as it's coming out. You're supposed to feel the flavor of this, okay? And then you're supposed to go think about it, because it is a big program. There's a lot of stuff inside this program. Now, I've told you about the language we're implementing, the pattern match substitution language. Showed you some rules. And I've told you about matching and instantiation, which are the 2 halves of how a rule works. Now we have to understand the control structure by which the rules are applied to the expressions so as to do algebraic simplification. Now, that's also a big complicated mess. The problem is that there's a variety of interlocking, interwoven loops, if you will, involved in this. For one thing, I have to examine every sub-expression of my expression that I'm trying to simplify. That we know how to do. It's a car-coulda recursion of some sort, or something like that, and some sort of tree walk. And that's going to be happening. Now, for every such place, every node that I get to in doing my traversal of the expression I'm trying to simplify, I want to apply all of the rules. Every rule is going to look at every node. And I'm going to rotate the rules around. Okay. Now, either a rule will or will not match. If the rule does not match, then it's not very interesting. If the rule does match, then I'm going to replace that node in the expression by an alternate expression. I'm make up a new expression which contains that new value, the result of substituting into the skeleton, instantiating the skeleton for that rule at this level. But no one knows whether that thing that I instantiated there is in simplified form. So I'm going to have to simplify that. So somehow I have to call the simplifier on the thing that I just constructed. And then when that's done, then I can sort of build that into the expression I want as my answer. Now there's a basic idea here, which I will call a garbage in, garbage out simplifier. It's kind of recursive simplifier. And what happens is the way you simplify something is that simple objects like variables are simple. Okay? Compound objects, well, I don't know. What I'm going to do is I'm going to build up from simple objects, trying to make simple things by assuming that the pieces they're made out of are simple. Okay? So that's what's happening here. Well, now, if we look at the first slide, overhead. If we look at the overhead, we see a very complicated program, like we saw before for the matcher. So complicated that you can't read it like that. Okay? I just want you to get the feel of the shape of it. And the shape of it is that this program has various subprograms in it. Okay? One of them is, this part is the part for traversing an expression. And this part is the part for trying rules. Now, of course, we can look at that in some more detail. Let's look at the first transparency. Right. The simplifier is made out of several parts. Now, remember at the very beginning, the simplifier is a thing which takes a set of rules and produces a program which will simplify relative to them. So, here we have our simplifier takes a rule set, and in the context where that rule set is defined, there are various other definitions that are done here, and then the result of this simplifier procedure is in fact one of the procedures that was defined. Simplify exp. What I'm returning as the value of calling simplifier on a set of rules is a procedure the simplify x procedure, which is defined in that context, which is a simplification procedure appropriate for using those set of rules. That's what I have there. Now, the first two of these procedures, this one and this one, are together going to be the recursive traversal of an expression. This one is the general simplification for any expression, and this is a thing which simplifies a list of parts of an expression. Nothing more. For each of those, we're going to do something complicated which involves trying the rules. Now we should look at the various parts. Well, let's look first at the recursive traversal of an expression. And this is done in a sort of simple way. This is a little nest, a little nest of recursive procedures. And what we have here are two procedures. One for simplifying an expression, and one for simplifying parts of an expression. And the way this works is very simple. If the expression I'm trying to simplify is a compound expression, I'm going to simplify all the parts of it. And that procedure, simplify parts, is going to make up a new expression with all the parts simplified, which I'm then going to try the rules on over here. If it turns out that the expression is not compound, if it's simple, like just a symbol or something like pi, then in any case I'm going to try the rules on it, because it might be that I want in my set of rules to expand pi into 3.141592653588979. ... But I may not. But there's no reason not to do it. Now, if I want to simplify the parts, well, that's easy too. Either the expression is an empty one, there's no more parts, in which case I have the empty expression. Otherwise, I'm going to make a new expression by const, which is the result of simplifying the first part of the expression, the car, and simplifying the rest of the expression, which is the cutter. Now, the reason why I'm showing you this sort of stuff this way is because I want you to get the feeling for the various patterns that are very important when writing programs. And this could be written a different way. There's another way to write simplify expressions, so there would be only one of them. There would only be one little procedure here. Let me just write that on the blackboard to give you a feeling for that. This is another idiom, if you will. Simplify an expression called x. What am I going to do? I'm going to try the rules on the following situation. If, on the following expression, compound, just like we had before, if the expression is compound, well, what am I going to do? I'm going to simplify all the parts. But I already have a coulda recursion common pattern of usage, which has been captured as a high-order procedure. It's called map. So I'll just write that here. Map, simplify the expression, down all the parts of the expression. This says apply the simplification operation, which is this one, to every part of the expression, and then make const those up into a list. Every element of the list which the expression is assumed to be made out of, and otherwise I have the expression. So I don't need the helper procedure, simplify parts, because that's really this. So sometimes you just write it this way. It doesn't matter very much. Well, now let's take a look at, let's just look at how you try rules. We can look at this slide. We see this is a complicated mess also. Well, I'm trying rules on an expression. It turns out the expression I'm trying is some sub-expression now of the expression I started with, because the thing I just arranged allowed us to try every sub-expression. So now we're taking in a sub-expression of the expression we started with. That's what this is. And what we're going to define here is a procedure called scan, which is going to try every rule. and we're going to start it up on the whole set of rules. And this is going to go cuttering down the rules, if you will, looking for a rule to apply. And when it finds one, it'll do the job. Okay, well, let's take a look at how try rules works. It's very simple. Well, scan rules. Scan rules, the way of scanning. Well, is it so simple? It's a big program, of course. We take a bunch of rules, which is a sub-list of the list of rules. We've tried some of them already, and they've not been appropriate, so we get to some here. We get to look at the next one. If there are no more rules, well, then there's nothing I can do with this expression, and it's simplified. However, if it turns out that there are still rules to be done, then let's match the pattern of the first rule against the expression using the empty dictionary to start with, and use that as the dictionary. If that happens to be a failure, try the rest of the rules. That's all it says here. It says discard that rule. Otherwise, well, I'm going to get the skeleton of the first rule, instantiate that relative to the dictionary, and simplify the result, and that's the expression I want. So although that was a complicated program, every complicated program is made out of a lot of simple pieces. Now the pattern of recursions here is very complicated. And one of the most important things is not to think about that. If you try to think about the actual pattern by which this does something, you're going to get very confused. I would. Now this is not a matter of you can do this with practice. These patterns are hard. But you don't have to think about it. The key to this, to very good programming and very good design, is to know what not to think about. The fact is, going back to this slide, I don't have to think about it because I have specifications in my mind for what simplify exp does. I don't have to know how it does it. And it may in fact call scan somehow through try rules, which it does. And somehow I've got another recursion going on here. But since I know that simplify exp is assumed by wishful thinking to produce the simplified result, then I don't have to think about it anymore. I've used it. I've used it in a reasonable way. I will get a reasonable answer. And you have to learn how to program that way with abandon. Okay? Well, there's very little left to this thing. All there is left is a few details associated with what a dictionary is. And those of you who've been itching to know what a dictionary is, well, I will flip it up and not tell you anything about it. Okay? Dictionaries are easy. It's represented in terms of something else called an A-list, which is a particular pattern of usage for making tables in Lisp. And they're easy. They're made out of pairs, as was asked a bit ago. And there are special procedures for dealing with such things called ASCII, and you can find them in manuals. I'm not terribly excited about it. The only interesting thing here in extend dictionary is that I have to extend a dictionary with a pattern, and a datum, and a dictionary. This pattern is in fact, at this point, a pattern variable. Now, what do I want to do? I want to pull out the name of that pattern variable, the pattern variable name, and I'm going to look up in the dictionary, see if it already has a value. If not, I'm going to add a new one in. If it does have one, if it has a value, then it had better be equal to the one that was already stored away. And if that's the case, the dictionary is what I expect it to be. Otherwise, I fail. So that's easy too. If you open up any program, you're going to find inside of it lots of little pieces, all of which are easy. So at this point, I suppose, I've just told you some million-dollar valuable information. Okay? And I suppose at this point we're pretty much done with this program. I'd like to ask about questions.
Yes, can you give me the words that describe the specification for simplified expression?
Sure. Simplified expression takes an expression and produces the simplified expression. That's it. Okay? How it does it is very easy. Compound expressions, all the pieces are simplified, and then the rules are tried on the result. And for simple expressions, you just try all the rules.
So expression is simplified by virtue of the rules.
That's, of course, true.
Right.
And the way this works is that simplify expression, as you see here, okay, what it does is it breaks the expression down into its smallest pieces, simplifies building up from the bottom, using the rules to be the simplifier, to do the manipulations, and constructs a new expression as the result. Eventually, one of the things you see is that the rules themselves, try rules, call a simplify expression on the results when it changes something. On the results of a match. The results of an instantiation of a skeleton for a rule that has matched. So the spec of simplify expression is that any expression you put into it comes out simplified according to those rules. Thank you. Let's take a break.